Um, Hello, everyone. Welcome back for the second half of day two. So we're going to start the afternoon session with a keynote talk by Hanie Sedghi. So Hanie is a senior research scientist at Google Brain, where she leads the Deep Phenomena Research Group. Her approach is to bond theory and practice in large-scale machine learning. Her primary research interest is in understanding and improving deep learning. Prior to Google, he was a research scientist at Allen Institute for Artificial Intelligence, and before that, a postdoctoral fellow at University of California, Irvine. Hanny got her PhD from University of Southern California with a minor in mathematics and her master's and bachelor's at Sharif University of Technology, Iran. There's a small change in the title of the talk, but it is, I think, roughly the same idea. So the talk is going to be about understanding transfer learning and its limits. So thank you for accepting our invitation, Hani. You can start.
Thank you for inviting me, and thank you everyone for attending. Very excited to be here with you all today. So, as Sarat mentioned, I'm excited about science of deep learning because I believe our understanding of modern neural networks lags behind their practical success, and this growing gap poses a challenge to pace of progress. Although there's been some progress in this area, we are still far from answering many fundamental questions, such as generalization capabilities of deep models, and also how to ensure successful transfer to new domains. And I believe this understanding would help us go beyond the current use of deep learning. And I work on principled approaches to investigate deep learning phenomena, or as we can call it, science of deep learning. And the goal is to understand when and why deep neural networks generalize, improve training and generalization performance in state-of-the-art deep learning models, and extend the current success of our models to new domains. So this talk is going to have two parts. In the first part, we're going to investigate what can and try to understand what's happening in transfer learning, or what is being transferred in transfer learning. And in the second part of the talk, I will talk more about exploring the limits of large-scale pre-training. So let's get started. So as we all know, one desired capabilities of machines is to transfer their knowledge or understanding of a domain it's trained on, which we call source domain or upstream, to another domain, which we call target domain or downstream, where data is usually scarce or we want a fast speed of convergence. And there is plethora of using transfer learning in different applications. In this work that I'm going to talk about, we investigated two questions. What enables a successful transfer, and which parts of the network are responsible for that? And this is joint work with my colleagues Benham and Chion from NeurIPS 2020. So just a quick recap of problem setup. We looked into target domains that are intrinsically different and diverse. So as an example of medical domain, we look into CheckSpurt, which is a medical imaging data set of chest x-rays, considering 5 different diseases, and also DomainNet, that you could see examples of it on the right-hand side, which has different domains, but the classes are the same. And there's 345 classes. And we consider two initialization scenarios. One is when we pre-train on ImageNet and we fine-tune it on these target domains, or when we start from random initialization and just train on these target domains. So the first thing that we investigated was the role of feature reuse. So as we all have seen this, when you compare the learning curves on different domains, we see that the largest performance boost comes from the domains that are closest to ImageNet. So in this case, like in real domain, which contain natural images. However, we saw that even for the most distant target domains, such as chest x-rays, plots, images, we still observe performance boosts from transfer learning. And the optimization speed when we are fine-tuning is much faster when we start, compared to when we start from random initialization. And the benefits of transfer learning are generally believed to come from reusing the pre-trained feature hierarchy. However, if it's just this, how are we still successful in many applications of transfer learning where the target task is very different from source task? So in order to answer this question, we designed this experiment. So we took these images of these domains that I talked about, and we partitioned the images of downstream tasks into blocks of different sizes, and we shuffled them randomly. And of course, as you can see in these images that I have here, it disrupts visual features. So here I have two examples. One is airplane, a natural image of an airplane, when we shuffle blocks of size 8 and shuffle blocks of size 1. So when you see, like, as you can see, when we shuffle blocks of size 1, this, like, the visual features are pretty much disrupted. And the other example I have is from quick draw domain, where we don't have any colors and it's just drawings, and what happens if we shuffle blocks of size 8. So what do we see in this experiment? So let's focus on these two plots that I have. So plot on top is about test accuracy versus as a function of the block size that we are shuffling. And the lower one is mean training accuracy, which is a surrogate for training speed, again, as a function of block sizes. Different colors are three different downstream tasks that we looked into. And let's look at the top plot. So the solid colors are random initialization, and the semi-transparent ones are when we do the fine-tuning. As you could see, excuse me, as we decrease the size of blocks, which means the more and more we shuffle and the more and more we disrupt these features, the performance drops, which says, yes, of course, feature reuse plays a very important role. However, the performance doesn't go all the way down to 0. So, and also if you look at the lower plot, which is the training speed, we see that it's still pretty strong even when we shuffle this when we shuffle these blocks and we mess up with random with the image features or visual features. So the takeaway, all in all, is that there are also other factors at play. So of course, feature reuse plays a role, but there are other factors, and that's why we do not get to I mean, not accuracy of 0, but like even random chance, and we still have the speed, the train in converging to a good accuracy. And we believe that low-level statistics of the data, such as histogram of the values, which are not ruined in the shuffling, lead to significant benefits of transfer learning, especially in the optimization speed. Another experiments that we did was about the loss landscape of these different models. As we all know, any two minimizers of a deep network can be connected by a nonlinear low loss path, and there's been a lot of work showing that. What we do in this paper is that we look into a series of models along a linear interpolation of the weights of the models. So in this plot, we essentially are looking at test accuracy as a function of linear interpolation coefficient. What does it mean? It means that I have two models and I linearly interpolate the weights. And at each of these linear interpolation points, I look into how this model performs on the downstream task. And what we expect to see is that performance barriers are generally expected between two unrelated neural network models because of the extreme nonlinearity we have. And when the two solutions belong to the same flat basin of the loss landscape, there is no performance barrier. So what we see here is that the purple line is essentially when we connect two fine-tuned models, and the red and blue show when we so blue shows if we connect a random initialization and a fine-tuned model, and the red shows if we just connect two random initialization models. And what we see is that the takeaway is that the fine-tuned models reside in the same basin. However, random initialization the models that start from random initialization end up in different basins, even if we start from exact same random seed. And the only difference is that the sequence of the data that they see is different. Another investigation we did was about the role of different layers. So we were inspired by this work from Chion and others, which is called Are All Layers Created Equal? So the experiment they do is that they take a neural network and they pick one of the layers and rewind its value back to a value at initialization and keep everything else fixed and look into how the performance changes. Their takeaway was that in a deep neural network, some modules, or we could think of a module as just a layer, are more critical than others, meaning that if you rewind their value back to initialization and keep everything else fixed, this results in a large drop in their network performance. But for many of the layers, this doesn't result into anything. Then the network performance remains pretty much the same. So We investigated this work, this analysis and this observation in our work at Utler 2020. And essentially, we mathematically modeled this, and we showed how we can figure out if a module is critical or non-critical, and how this relates to generalization. So essentially, what we did was that we look into loss values in the values that connect the initial and final base. So what we see in this plot is that the x-axis is essentially the linear interpolation coefficient that connects the final theta f to initial theta 0 values. And then as we're walking on this path, we add Gaussian noise to have a two-dimensional, essentially, view of what happens to the loss. So what you see on the left is a non-critical layer, meaning that when you go through from final value to initial value, you still have quite a wide valley. And what you see on the right is a critical module when the valley gets tighter and tighter as we try to go from final to initial value, meaning that the model is really disturbed when we change the value of this layer. So essentially, yeah, this is the non-mathematical way to put it. But of course, feel free to look at the paper for mathematical details of this. But for the sake of this talk, I want us just to take away this. Non-critical modules are lead to wide valleys in loss landscape, and critical modules lead to sharp valleys. And we showed in this work that module criticality is a really good generalization measure, and it correlates well with model performance for different architectures. So what we see here is that we looked into module criticality in the transfer learning setting. And we saw that as we go from lower layers to top layers, so here on the left, you see module criticality of layer 1, and on the right, you see module criticality of layer 4, and we see that the valleys are becoming tighter and tighter, with sharper and sharper. So essentially, and apologies for that question mark, but so this is in agreement with observation of Yosinski and also Ragu from 2019, I believe, that lower layers are less. So what does it mean where lower layers are less critical and higher layers are more critical? It means that lower layers are in charge of more general features. And that's why we see this phenomena here, but higher layers have features that are more specialized for the target domain. And because of that, because they're more specialized, if we rewind the value of the fine-tuned model to the initialization, which is the pre-training model, we see that this serves the performance more. So this is a more critical layer. Okay, so what did we talk about so far? We showed that both feature reuse and low-level statistics of the data are important. And we also showed that there is no performance barrier between fine-tuned models, while models trained from random initialization are in a different Bayesian in a loss landscape. We also showed that lower layers are in charge of general features and higher layers are more sensitive to perturbation of their parameters. Excuse me. So there's a lot more investigation in this paper, and I encourage you to take a look at them. But for the sake of this talk, I'm gonna just talk about these and switch over to the second part of the talk. So if for whatever reason I've lost your attention, here's your chance to come back and hear about the second part of the talk. So okay, so in this work, we look into exploring the limits of large-scale pre-training. As we know, there's been impressive progress recently in transfer and few-shot learning that has happened due to scaling up model and data size. And there's so many prominent examples. A couple of them are like GPT-3 and CLIP, and there's massive data sets such as Instagram images and JFD300. So for those of you that don't know about JFD300, JFD300 is a Google internal data set that has 300 million images and 18K classes. The other data set that we are going to look into, which is publicly available, is ImageNet 21K that has 21K classes and 15 million images. But back to this recent results, it seems that the current narrative is telling us two things. Excuse me for 1 second. That Scaling up model and data size improves performance significantly. In addition to that, the performance improvement transfer to downstream tasks in a desirable way. What do I mean by this? It means that the current narratives seem to tell us this story that keep getting better on your pre-training, and this is going to just transfer to whatever downstream task you have. And there is just no saturating performance, just everything keeps getting better. So in this work from Cornbit et al. In 2019, we actually see this observation that they look into accuracy. So what does this plot tell you? So the y-axis is accuracy on pre-training, and x-axis, is accuracy on the target domain, and x-axis is accuracy on pre-training. And they look into 12 different data sets here, and they see that there seems to be a linear relationship between downstream versus upstream performance. And the pre-training they have is ImageNet-1K. However, this wouldn't be the complete story if, like, I'm here today to tell you that this is not the complete story, and that's why the second part of the talk is especially focused on this. There's shortcomings about related these earlier works that I talked about, and one is that performance for different choices of hyperparameter values are not reported. So each of those dots in this plot is one architecture and one set of, and that's it. So for each architecture, they just have one point. However, when we are studying scaling, we are concerned about the best performance of the model given all possible values for hyperparameters. The other limitation is that there is limited accuracy range in this plot. Another shortcoming of earlier works is that many of us just focus on improving SOTA, and we have limited computational budget. So we really cannot cover all the ground. However, simply extrapolating scaling without understanding of dynamics of scaling can be detrimental. We can't just say, okay, there we have this line in this limited hyperparameter and limited accuracy range, and so it's just going to keep being a line. And that's why we essentially did this work. We did a systematic larger scale study to investigate how does improvement on a larger scale upstream task transfers to a wide range of downstream tasks. We looked into close to 5,000 experiments, and these are all on image recognition tasks. The architectures that we looked into were vision transformers, ResNets, and MLP-Mixers of varying sizes. The model sizes range from 10 million to 10 billion parameters. And the pre-training data is JFT and ImageNet-21K, and we have more than 20 downstream tasks. We did our best to cover a wide range of standard data sets, such as VTAB, metadata set, WILES, and some medical imaging data. The plots that I show you in this talk are when we look into especially like few shot setting, but in the paper, we have also included this phenomena when we do fine tuning. Throughout the rest of the talk, I'm going to keep showing you plots like this, where y-axis is the downstream or target accuracy, and x-axis is upstream accuracies, and US is abbreviation for upstream. We're not talking about USA. So what is our goal? Our goal is to predict downstream performance for a given model, and we have a bunch of models that were trained, and we looked into their downstream versus upstream accuracy plots. And this horizontal line, I'm just telling you a sneak peek of what's going to happen, is the predicted accuracy as upstream accuracy becomes 1. And we provide a mathematical model in the next couple of slides, and I'll tell you how we come up with that. But essentially, each of these dots you see in this plot are a different model pre-trained on. In this plot is JFD specifically, and they look into their few shot performance on cars. But there's 20 data sets that I'm going to cover. But before we get into additional mathematical details and additional experimental investigation, let's do a quick recap of a convex hull. And apologies, I know like convex hull is a very well-known very well-known definition, but just to make sure we're all on the same page. Okay, so if you have n points, a sub j, in a set S, their convex hull is essentially given by weighted sum of them, and these weights are shown with p sub j, where the weights are non-negative and they sum to 1. Okay, but why do I tell you about this? Is because I can easily prove this lemma, which is as follows. Let's say I have a group of models that can be neural networks, and they have accuracies a sub j, where a sub j is this couple a sub j upstream and a sub j downstream. So these are essentially points on a two-dimensional space, and you're essentially looking into some pairs of upstream and downstream tasks. I can construct a randomized model tilde tilde as follows. For whatever input you give me, with probability p sub j, I pick model j and output the output of model j on this input. Essentially, then I can prove that this randomized model will demonstrate accuracy, which is weighted sum of these a sub j's. Okay? So given n models that have upstream downstream accuracy pairs, I can construct a randomized model that can have the accuracy corresponding to the convex hull of these points on these 2D plots. Why do you have to care about this? Is because there's good things about convex hulls. So as you saw in the plot, we have larger variance across different models, and we want to make sure that we are robust to the density of the points on the plot. And the reason we want to be robust to that is that these models that we have on that plot were already trained by another group, and we wanted to investigate them. So they hadn't done a complete swap, and we want to make sure we are actually capturing the phenomena. And so if you just fit the existing points, you're fitting the average performance. If you fit the upper convex hull, we fit the best performing model. And that's what we're really interested in. We want to see best case scenario, what's going to happen to my downstream accuracy as the upstream accuracy gets better and better. And as I mentioned, this is robust density of the points. And because of that, we consider the convex hull of the points in our analysis. And that was the line you saw, the curved line that you saw in the plot that I showed you. Okay, back to the story. So here I have downstream y-axis versus upstream x-axis accuracy for 8 of these 20 data sets that I mentioned. And different colors show different model architectures. So blue is vision transformer, red is ResNet, and green is MLP-Mixers. And the model sizes are shown with the size of the circle. And these curved lines are the convex hull fit to these models. And again, the horizontal line is our prediction of what would be the best case that happens to downstream, which is, and by best case, I mean if upstream accuracy reaches value of 1. And I'll get into that in the next couple of slides. Okay, so now that I talked about all the details of the plot, let's zoom out. What do we see? We see a saturation phenomenon, meaning that even if upstream accuracy reaches value of 1, downstream won't. So if you look at all these plots, this horizontal line is not at 1. And because of that, there is a nonlinear relationship between downstream and upstream accuracy. Okay, so the plot that I showed you was for pre-training on JFD and for 25 shot. We looked into pre-training on ImageNet 21K and also one shot. So the lowest one, which is the green one, is JFD one shot, and then JFD, is ImageNet 21K one shot. The orange points are ImageNet 21K 25 shot. Purple is JFD one shot, and magenta is JFD 25 shot. So what do we see? We again see the saturation phenomena, and it's consistent across different upstream tasks and number of shots. Now, as I promised, we're going to mathematically model this. Why do we want to mathematically model this? Again, as a recap, we want to predict downstream performance given the upstream performance of whatever models we've had so far. So the purple shows the model that we propose. I don't know if you see my cursor, but E sub ds is the error on downstream task. K is the constant. E sub US or upstream is the error on upstream. Alpha is another constant plus E sub infinity. What is this E sub infinity? We call it irreducible error because it captures the value of downstream accuracy if upstream error gets zero, right? So if upstream error gets zero, this is zero, and we have E sub downstream is E sub infinity. And essentially, this is capturing the nonlinearity because if E sub infinity was zero, you could take the log and then you could see this linear correlation. However, it's non-zero. That's what we're telling you. And it's not the base error. Why is it not the base error? And for just as a recap, base error is the intrinsic error corresponding to downstream accuracy. Why is it not base error? Because we do this additional experiment that we change the number of shots and then change the number of upstream and downstream tasks. And we see that E sub infinity changes when we change these things. So, and there's additional information here, which essentially we look into how these constants correlate with number of shots and also correlate with upstream and downstream tasks. So we see that as the number of shots increases, E sub infinity and the K constant get they decrease, so correlate negatively, and alpha is positively correlated. And correlation values, as you could see in this table, change drastically for different choices of upstream and downstream tasks. Okay, so E sub infinity, if you want to just take one sentence from this whole slide, is that E sub infinity is not the base error. It changes as we play around with upstream data. Okay, the other thing that we do is that, so we propose this power law, essentially mathematical model to predict downstream performance. Now we investigate how does this prediction error change when we change the sample size, because, okay, we had about 5,000 points on that plot, but what if we have less? Can we still use this, or we are just going to be able to use it for a really big number of samples? So here we look into prediction error and fitting error. So what we do is that we give this parallel model the values of the lower part of the plot, and we ask it to predict the values on the top part of the plot as tests, and we see how does it predict and how does it fit them, these points that we have. And essentially the takeaway here is that even if we go all the way down to that sample size of 100, the error is in prediction error, and also the fitting error is pretty small. And also the colors here, so the blue and orange show when we fit all the points, and red and green shows when we fit the convex hull. And as you can see, the convex hull, it works even better than when we fit all the points, even if we ignore whatever I told you about why convex hull is good. Okay, so good news is that this mathematical parallel model works well even if you have 100 model trained. You don't need all these experiments that I told you about. Okay. So what I talked about so far, as I mentioned, was 5,000 experiments that other people had done when they were trying to find, when they were essentially running experiments on vision transformers and MLP mixers, and we found this phenomena that we have this saturation and nonlinearity. Next, we did controlled experiments ourselves. We took a closer look. We took these models and we played with 3 dimensions: model size, data size, and compute. And by compute here, I mean the number of epochs we pre-train on the pre-training data set. So what we see in this plot, again, the famous downstream versus upstream accuracy plots, the gray dots are the dots that we saw from those 5,000 experiments, and the colored ones are these controlled experiment models. So what does this refer to exactly? So different colors show different model sizes. We go from 9 million to 324 million. Different shapes show the number of epochs. So circle is 7 epochs, rectangle is 14 epochs, and you get the gist of it. And the transparency shows how much data size you have. And again, data size here is pre-training data size. Okay, so what are the takeaways from these plots? You see the same pattern in the colored and gray ones, meaning that when we do these controlled experiments, we still see this pattern of saturation happening. And we also see that there's the same curve for all these 3 parameters that we are changing. All these colored ones are really on the same curve, so we don't need to change all 3 of them. We can just play with one of them, and we can still find our curve. And that means that because of this, we have research equivalence from what we saw earlier. So we really didn't need to like check everything. And the other interesting thing is that we see this variation around, like we see these gray points are scattered around the colorful ones. Why does this variation happen? These are due to training hyperparameters such as how you schedule your learning rate, how do you do your initialization, what is your optimizer, and so on. Okay. Next, next, I think I prepared you for this next statement that I have, which is we saw that all these 3 dimensions that we play around when we look into scaling are leading to one curve, right? And in earlier works on scaling law, they always look at the effect of the scale separately on these 3. But we see that in transfer learning, we really don't need to look at these separately. What am I showing you here? So we look into the prediction power of the upstream accuracy for downstream accuracy. And so this, so each of these colors is just different number of shots. So for sake of this plot, you could just pick a color and look into that trend. And what we see here is that what is the downstream accuracy if I only use upstream accuracy and look at the standard deviation of the error, and it's really small, as you could see this noisy part, so that's our error. So if you want to take away one thing from this slide, is that conditioned on upstream accuracy, there is really not much left for the rest of the parameters altogether to predict downstream accuracy. So essentially here, I'm just doubling down that you only need to look at upstream accuracy. You don't need to look at 2, 3 parameters separately. Okay. Now, the next thing that is interesting in all these plots that I showed you is that different downstream tasks had different, if you go back here, different downstream tasks have different, essentially, reaction or trends in upstream versus downstream. So, for example, if you look at ImageNet on the top, third from the left, we see much more stable and later saturation happening versus when we look at Caltech, which is right below it, it saturates much faster. So in the next part of the talk, I'm going to investigate why do we have these differences? Can we learn something from it? Can it give us a takeaway in how to pre-train and things like that? Okay, so the first thing that we do is that we, so again, again, we're looking into downstream versus upstream accuracy. Again, the gray points are the points from the 5,000 experiments. And what we do is that we overlay best performing image models versus the essentially convex Hall of ImageNet developers versus all the other downstream tasks. And we look into 2 different shots. So the dotted lines are 25 shot and the solid line are 1 shot. Red is ImageNet, blue is whatever else that we are looking into. So here we are looking at convex Hall of PETS versus convex Hall of ImageNet, convex Hall of C400 versus convex Hall of ImageNet. What do we see here? First, we see that convex Hall of these things do not sit on top of each other. So if something works great for ImageNet, it doesn't mean that it's the best model for C400 or Caltech or whatever. And but for many of these downstream tasks, there is a lot of similarity. And also, as the upstream accuracy increases, the gap between these best performing emergent models and best performing other downstream tasks reduces significantly. Now, we do this experiment that we overlay downstream versus upstream performance to another plot, which is this red triangles here. What is this red triangle is that we move the head to different layers. So when we have this few shot setting, we have essentially, what do? We pre-train, we discard the head, we put another head on top, and we have just a linear classifier that we train. Now, instead of putting the head on the last layer, what we do in this experiment is that we try to put the head on different layers. So we are essentially looking into what is the feature power of different layers. And now what I talked about in the first part of the talk comes handy. But before getting into that, let's look at these plots. So y-axis is again downstream accuracy, x-axis is upstream accuracy if you look at the green one, and it's if you look at the red ones, it shows which layer you put the head on. What do we see here? We see that these plots have similar trends. And for downstream accuracy, for downstream data that saturates faster, higher layers are not needed. Let's take a look at one of these examples. So if you look at cars here, top right side, you see that the triangles, the red triangles for the when we put the head on later layers, they're all about the same height, meaning that it doesn't really matter these top layers. The accuracy doesn't change if I discard them. But for example, for let's look at ImageNet, which is the one right next to it, you see that like the trend is still that we seems to need all these layers, because as we change the head to lower layers, the accuracy drops. But remember from the first part of the talk that lower layers capture lower level features that are more common across different data sets, whereas fine-grained features that are related to more fine-grained features are in top layers. So what does this mean? It means that these top layers are capturing features that are irrelevant for many of these data sets. And if you want to remember one thing from the last 10 minutes is that we need data diversity, because we need to capture those features if you want to have good downstream performance, if you want to have better downstream performance that saturates much later, that essentially the later we saturate, the more we can gain on downstream before we stop improving. Okay. Now, I'm going to talk about another interesting phenomenon that we really liked, and I hope you like it as much as I did. So remember when I showed you this plot that training hyperparameter caused this deviation from the curve that we get if you only change model size, data size, and compute? Now, for the next couple of minutes, I'm going to focus on the effect of hyperparameters. And especially, we're going to focus on effect of head hyperparameters. Why head? Because as I mentioned, as the pre-training is done, and whether we do few shot or fine-tuning, we discard the head, we put another head, because the number of classes usually don't match, right? So, and that's why we focus on effect of head, and we decouple head from the rest of the network, meaning that when we are pre-training, we have a different rate decay for the head and different learning rate for the head, for example, as for the rest of the network. Okay, and we specifically look into these, as I mentioned, weight decay and learning rate for the head. The plots I'm going to show you capture the weight decay, the phenomena that we see when we change weight decay. If you want to see the ones corresponding to learning rate, you could take a look at the paper. Okay, what do we see? Here, again, we have our famous plots. 4 different colors means 4 different values of few shots, number of shots for the few shot setting. Just pick one color and look at that. And the gray one shows what happens to upstream performance when we increase head rate decay. Okay. So the green one, so the colorful ones are downstream accuracy as a function of head rate decay on the pre-training data. And the gray shows the value of upstream accuracy. What does it mean? Okay, when we go from left to right, we are increasing head weight decay. And if you look at one of these gray plots, you see that increasing head weight decay is decreasing the performance of upstream. However, for some of these upstream tasks, let's take a look at, for example, ImageNet, when we change the head weight decay from 0 to 1, the accuracy in downstream is improving. So there is this mismatch. We are making upstream worse, but downstream is doing better. What's really going on? So in order to investigate this, we look into two things: layer margin and layer norm. So layer margin was essentially the notion of margin that we have in the last layer. Now, this is like the general notion of margin, but they define it for all the layers. And both margin and norm are the values that theoretically we as a community have shown that they relate to how much information is stored in a layer. So now let's look at the plots. So the one on the left shows L2 norm of head and L2 norm of different layers as we increase the head weight decay. So the blue shows the L2 norm of the head. We see that L2 norm of the head is decreasing versus if the red one shows the L2 norm of all the other blocks, and that's pretty much increasing. And then the one on the right is margin. So again, the green one is for the head. The margin is decreasing as we increase the head weight decay versus the pre-logit layer, which is shown in orange, is increasing. Okay, what does this mean? It means that as we are increasing the head weight decay, we are pushing the information down to lower layers. That's why the norm of head and the margin of the head are decreasing, and the lower layers are now having more information. That's why the margin and norm are increasing. But why is this good for some downstream tasks is that they care about that information that is stored in the head, and when we push that down, they're essentially using it for their tasks versus for some of the data sets, we see no difference. So again, those are the data sets that we saw, these top layers are irrelevant. But for ImageNet, as we saw, it's the closest to JFT, and it matters what we do for the how much information we can preserve. So all in all, this is just one example that shows that there is no one checkpoint that's great for everything. It really matters what data sets that we have. And we really encourage everyone to, when we are thinking about scaling up and we're investigating and using money to do all this scale up, think about other downstream tasks too, and not just look at ImageNet. That's like the standard way people go about it, which we're just trying to say here that let's not do that. Okay. For the sake of the time, I'm not going to talk about all the experiments we have in the paper and all the plots. I'll show you all the plots. And I encourage you to look at them and reach out. We'd be delighted to chat. But here, just give you a recap that we changed the number of shots. We also looked into transfer versus few shots. We scaled the plots in different formulas that people in the community have done. We looked into logit, minus log of 1 minus p, and linear. And in all these scenarios, the phenomena that I told you about today stay the same. And also, we see the same phenomena when we change the architecture. So this is not just about vision transformers. It also is the same for ResNets and also MLP-Mixers, which are very different architectures, these three. So in summary, in the second part of the talk, I talked to you about a large-scale systematic study, and we look into downstream versus upstream accuracy, and we observe that performance saturates on downstream as we keep improving upstream. We modeled it with a parallel curve, and we show that its prediction is really accurate, and you don't need a lot of sample size. Even with 100, you get really good prediction power. I emphasize again that data diversity matters when we are doing pre-training, just increasing the data. If the distribution is not changing, it's not going to bias much. And scaling model size, pre-training data size, and compute leads to the same curve. I also showed that upstream performance has high prediction power, so we don't need to look into these three dimensions separately. Again, I emphasize hyperparameters used in pre-training matter. They need to be downstream specific. For different downstreams, we have different upstream hyperparameters that are good. And in the paper, we actually have a lot more plots on that. And also, of course, head hyperparameters are important, and they can help improve downstream performance even if they're hitting upstream hard. This work was spotlighted at ICLR 2022, and it was collaboration with my former students, Samira, and my colleagues, Mustafa and Enam. Okay, what's next? I'm just going to spend one slide talking quickly about this. So if it's super simplistic way of thinking about what's happening is that you're sampling data from universe and training it on a deep neural network model. It would be great to get feedback from our deep neural network model to improve our data sampling. It would be great for us as a community to be able to model the data better, ensure the data diversity. I already mentioned closing the loop. And as the data increases, not all the data is created equal. Can we look into effective curriculum learning so that we don't need all this data? We can just choose a subset and like have a specific sequence on that. On the deep neural network model, I think uncertainty estimation for auto distribution generalization is really important. Adaptive architectures are giving us a lot of benefits. And as we saw, like there's like these different layers have different roles, and it would be great to get feedback from downstream data and adaptively change the architecture, and of course adaptive training for making sure we have auto distribution generalization would be a great thing to do. With that, thank you so much, and I'm happy to take questions.
Thank you. Thank you for the great talk. So questions, maybe I'll start with one question from the remote participants. What exactly was your upstream task? Was it a self-supervised learning loss?
That's a good question. So here, in order to make sure that we are not adding more complexity, both upstream tasks and downstream tasks are just classification tasks. We did not look in this work. We did not look into effect of self-supervised versus supervised, but we have a current work that hopefully we're going to submit to ICLR that will look into self-supervised learning, and that's with my collaborators at UW.
Okay, thank you. Any questions from the audience?
Thanks a lot for the talk. Great talk. I have a question about the first part of the talk, which is to what extent do you think the results that you have are architecture specific and model size specific? In particular, I'm wondering of the role of overparameterization in sort of how these law surfaces look.
So we are in the overparameterized regime in all these experiments that I told you about today. We do not make any claims for the underparameterized regime. And I don't know if that answers your question.
It does, but have you explored like different model sizes? I mean, like, does it matter how overparameterized you are? Like, I don't know, did you observe any kind of effect if you change the model size at all?
So the models that we looked into the first part are ResNets of different sizes, and the observations didn't change with the model size. And I know some follow-up works that looked into models that were bigger and they still observe similar things.
Okay, thank you.
Sure.
Any other questions? Maybe I'll follow up with another question. Again, on the first part. So you talk about criticality, where you define it using Gaussian noise. I don't know if this makes sense, but I'd assume that for any of those things, if you look adversarially for the smallest change that you can do, would you be able to distinguish between layers? I would imagine you could attack any given layer with an equally small epsilon. Is that something you thought about? Do you think that plays a role?
That's a very good question. So what we were interested in was like general generalization, and the reason we look into Gaussian noise is that because this definition of module criticality is inspired by Bayesian approach to finding capturing phenomena in generalization, and we did not look into adversarial parts. And the reason was that we weren't looking into what would it mean in terms of adversarial robustness of the network. But that's a very good question. I haven't thought about that. I'll think about it more and I'll follow up.
Okay. Thank you.
Thank you for the great talk. I'm not really sure if this question is relevant, so but still. So, do you think there's any overlap in the downstream task with the upstream, and if there could be any effect based on the overlap in the data sets from upstream and downstream tasks?
You mean duplicates in samples or overlap in the distribution?
Let's just say that features of the model that are coming from upstream training, which can be helpful for downstream training.
Yeah, of course. Like that's what I was talking. Like that's what essentially we mean by feature reuse. There are some features that the model learns from pre-training that are being reused to be able to have performance in the downstream. And that plays a really important role in transfer learning. That said, it's not the only player. Like this low-level statistical data and are also player. But yeah, feature reuse is a really big chunk.
Thank you.
Hi, Hanie. You mentioned self-supervised learning. I guess this is work you didn't talk about today, but could you say a little bit more if you did your upstream self-supervised? Is that like a more robust feature representation for downstream tasks?
It seems, at least, I mean, we haven't finalized all our investigations, but it seems from what we see so far, it seems like self-supervised learning is on upstream works better than compared to just supervised one. But I'll follow up with you on that, Kevin, once we have all the experiments resulting.
Okay, any other questions? Okay, well, there are some questions in the chat actually.
Okay.
And just
trying to stop sharing my screen.
Okay, I can ask them for you. So, did you find any catastrophic forgetting or interference in these experiments?
That's that's a good question. I think we didn't look into that because we are just looking to pre-train or and looking to fine-tune, and but we didn't jump from one downstream to another downstream task. But that's a very good question to look into. And in terms of interference, we didn't really look into that. That's a good question.
Okay. Okay. So, like, probably one more question. So, okay, I'm trying to. Well, the question is very brief, so I'm trying to expand it. So, like, can we use some of the things that you talked about upstream to downstream performance as a measure of task similarity?
Yeah. So essentially, we do that. I didn't have it in the plot in the talk, but one really easy measure of task similarity is when we have a bunch of these models and we look into ranking of upstream versus ranking of downstream accuracy, and this just gives you a correlation coefficient. As simple as that. More complex way of thinking about it is that the more layers of upstream that network that are useful for your downstream task, which I showed in this plot. I don't know if you guys still see my screen or no.
No, I think he stopped sharing, but you can.
Okay. Yeah, let's share my screen again. Okay, so if you look at this plot here, essentially for downstreams that these top layers are still useful, like here in like ImageNet, it means that they're more similar, meaning that more layers and more representations are essentially needed for the downstream. So that's another measure of task similarity. There is this work from my colleagues at Google that they have this two-level chain. They pre-train on ImageNet, fine-tune on something, and then look into few-shot performance. And they also have a notion of task similarity. I don't remember the title, but I'd be happy to send it, find it and send it afterwards. But yeah, so in this work, these are the notion of task similarity that we have. Yeah.
Okay, thank you.
Sure.
Okay, we have one last question.
Sure.
Oh.
Thanks for the talk. Yeah, I wondered if you think that it's possible that, in this saturation kind of behavior that you described, if actually the models which are which have the higher accuracy on the upstream task, would be less plastic than the models which did not get this high accuracy, and if this could explain part of what you've seen.
What do you mean by the models being plastic? I'm sorry, I don't understand that part.
Well, kind of, the the plasticity, rigidity dilemma or something like that.
So you mean, so if I understand your question, so what you're saying is that the models that have higher accuracy on upstream are less rigid to be changed for downstream tasks? Is that what you're saying?
Maybe over specialized. I don't know.
So what we see here is that it can explain what we see, that the top layers are more specialized. So the more you're specialized, but yeah, I don't see a clear connection here. I need to think more about it.
Okay, thank you.
Sure, but feel free to reach out. I can chat more after.
One last question and then we'll finish.
Hi, thanks for a great talk. Yeah, sure. I should finally read your paper carefully. But yeah, so I guess the question was related to the previous. Indeed, I mean, we were discussing whether there is something just like with good old overfitting issue, right? So in a sense, analogy here is that on pre-training data, it's just like on training, you achieve good performance on those upstream tasks. Of course, they are not on same data, they are in validation anyway, but it's still the higher level, but analogy with overfitting. And then on the downstream tasks that are presumably much more different from the upstream data, you see performance. And the question is there something analogous to the overfitting phenomena? And I think that's what the previous question was trying to, like, so if you really performing extremely well on upstream tasks, does it mean that you're likely to be more rigid or less adaptable on the downstream task? But
I
adaptation
see.
also can be done in different ways. And one thing is just to keep fine-tuning with SGD, or another is to do something else. And that's where
I
we
see.
get into continual learning. And people
Got
do try to use a little bit of replay, like in this ACL paper, like 1% of old data, and the system keeps continual learning without any degradation of performance on the
I
upstream task.
see.
So I was just curious about like what your intuitions. Is that
Right.
a trade-off? And do you think that some tiny maybe amount of replay from old pre-training data could have kept the system kind of at a
Right.
better trade-off? Yeah.
Right. So one thing that I need to mention is that here we are. So when we are doing few shot, we're just training the last layer. We're not changing anything from the backbone.
It's no
When we
fine-tuning.
do there's no fine tuning. But when we do fine tuning, the experiments that we have in the paper, and I didn't talk about here, we do not go as far as just keep doing SGD until the effect of pre-training completely disappears and see how things change. So that's one thing I wanted to mention, so that this framework essentially doesn't fully capture the question. But the other thing is that sometimes those features are just, so of course there's just top level features, top layer features that are irrelevant for some data sets, not irrelevant for all of them. So for ImageNet, for example, that if ImageNet 1K is downstream, they're relevant, they're needed. So let's keep becoming better at JFT. But for some downstream tasks, they're useless, essentially because the data does not even exist in the pre-training. So even if we keep learning and learning the pre-training data better and better, or if you replay them, we don't have that feature present in the upstream data. So for something like UC-Merced or CARS data set that they saturate really fast, we need to really diversify our pre-training data to make sure we're capturing something that they need. Or we need to, for example, re-weight some of the samples. So for example, CARS is all CARS, but JFT has a lot more diverse things. So maybe if for CARS we replay, we can look into like what happens if you replay similar images only and see what happens. Yeah,
Okay,
but
thank
I don't
you.
know if that's going to be cheating. Anyways, sure.
Thank you.
Okay, let's thank the speaker once again.